AP Chemsters, this is Mrs. Vanderlei bringing you Blankwalle 6.3, Part 2. So if you go back and kind of review what we did in section 6.3 already, we've talked about these sign values, these positive and negative values of Q, W, and E. And the thing that you really need to know that if any of those values, let's say, are negative, that means something's going from the system to the surroundings. So if Q is negative, heat flows from the system to the surroundings. If work is negative, that means it goes from the system to the surroundings. So it's like pushing up to the surroundings. If delta E is negative, that means just the total energy flow goes from the system to the surroundings. And the reverse will also be true. If they're positive, everything flows into the system, okay? So we're looking at an example of how this works. So it says a billiard ball is rolling on the table. When the first billiard ball hits the second billiard ball, the first one stops and the second one starts moving. The energy lost, say it again, the energy what? The energy lost by the first billiard ball is lost to the surroundings. Observation, the second billiard ball doesn't go as fast as the first, okay? So a couple things already noticed that the energy is lost. So if I call the first billiard ball is my system, okay, because the energy is going, from the billiard ball to the surroundings, so my system is my billiard ball, what does that probably mean when I'm all done? What do you think that delta E for the first billiard ball is going to be, positive or negative? What do you think? Did you say negative? You're right. So let's check this out. Well, before we get started, what are the surroundings? All right. So notice it's even a plural. What are? Because there's more than one surroundings. Is the second billiard ball a surrounding? Yes, it is. But there's something else, especially when it says there's an observation. The second one didn't go as fast as the first. Well, why not? Where did some of that energy go? Can you think about that? Well, I said this, the table is also the surroundings because there's some friction from the surface of the table to, the friction, and it goes to the table, okay? So we have something here. The E of the system is negative E of the surroundings, okay? So what is this saying is that the amount of energy lost by the system is the exact energy gained by the surroundings. But why is there a negative sign? Because if this is a negative, and if the delta E of the surroundings is gaining, it's a positive, in order to make it equal, you need a negative in front of it. And we're going to see this over and over again as well, okay? So what is the E of the system? Do you remember, remember what E is defined as? E is defined as Q plus W. What did we define Q as? Q is heat, remember that? What's W? That's work, okay? So it says over here the initial kinetic energy is 5. Heat lost, see that? Lost is 0.5. And the kinetic energy at the collision is 4.5. So if it's heat lost, what does that mean Q is? Is Q positive or negative? This is the system, remember. Q is going to be negative. Why? Okay, because it is... Well, let's just kind of do that here. Heat is lost. Oops, sorry, wrong one. There we go, that's what I want. Now, what else is there to be had? What about the work? It goes from the ball to the second ball, okay? So this is your table with the heat. Well, what is getting the work from the first billiard ball? It's the second, your second billiard ball. Come here. There we go. All right, so I have this. Okay, why is that positive or negative? Because work is done by the first billiard ball, isn't it? Okay, so it's also a negative number. So if I were to put all this stuff together, what's my delta E of the system? It's negative 5 joules. What about the surroundings? Well, what do you think the value of the surroundings is going to be? Well, E of the surroundings is what? Negative times negative 5, and that means positive 5. And so what does that mean? That it gained 0.5 joules of heat. It gained 4.5 joules of energy. So it's a positive. And what else do you notice here? The second or the first one stops, right? So if it started out with an internal energy of 5 joules and then it stopped, that means that it lost all 5 joules. It lost all 5 joules. So that means that the surroundings gained all 5 joules. Okay, hopefully that makes some sense, but that's a smooth table. So what do you think is going to happen when we get to a rough table? Let's check this out. So we have a rough table. So the coefficient of friction here is a little bit higher, isn't it? So your heat lost is 3, right? Your work done, that means the energy at collision is going to be 2, but that means that your surroundings gained that much energy. If the surroundings gained, your system lost, right? So here we go, and what happens? You still get -5, no matters what, right? So what do you notice about the delta E values? Oopsies. Well, they are the same, okay? Does that make sense? I sure hope so. What about E of the system? What do you notice about E of the system? It's still -5. What about E of the surroundings? It's still +5, isn't it? Okay, so again, this is all having to do with the law of conservation of energy. We didn't, lose any overall to the universe. Whatever was lost was gained. So it was lost by the surroundings, or by the system was gained by the surroundings. Okay, let's go to the next page. All right, so identify each energy change as heat or work, and determine the sign of the heat or work relative to the system as positive or negative. So the ice cube melts and cools the surrounding beverage. So the ice cube is the system. So is the ice cube giving off heat or absorbing heat, I guess, or is it doing work? What do you think? Well, I think it's heat. So is it positive or negative heat is the question. So if ice cube is a system, it's going to melt. It has to be a positive cube because it's gaining energy in order to do so. So the ice is gaining heat from the surroundings, the beverage, right, causing the ice to melt. Okay. So what about the beverage? The beverage gave its heat to the ice, and then what? The beverage actually will get colder. Okay. So the metal cylinder is rolled up the hill. Is this heat or work? What do you think? Hopefully you said it's work, and it's positive work, right? Why is it positive work? Because the work is done on the cylinder by the surroundings, probably you, causing it to go uphill. So what about steam? Steam condenses on the skin, causing a burn. So what will it be? Is it thermal? Is it heat? Or is it work? Well, hopefully you said it's thermal, okay? And why is it negative? Because it's giving energy to you. You are absorbing that energy from the steam, okay? So it's causing a burn, meaning it's getting hotter on you, it's burning you, okay? What about letter D? You get out of the shower and you are cold. The water droplets on you is the system, you are the surroundings. So what's happening here? Is it a heat or a work? Hopefully you said it was a heat. And why is it a positive? So what's happening? The water droplets are gaining energy from you so that it will evaporate. You are losing heat to the water droplets and you feel cold. Okay, let's look at the next example. Okay, the firing of a potato cannon provides a good example of heat and work associated with a chemical reaction. A potato is stuffed into a long cylinder that is capped at one end and opened on the other. Some kind of fuel is introduced under the potato and capped at the end, usually through a small hole, and ignited. The potato then shoots out of the cannon, sometimes flying hundreds of feet, and the cannon emits heat to the surroundings. If the burning of the fuel performs 855 joules of work on the potato, produces 1,422 joules of heat, what is the delta E for the burning of the fuel? Note, a potato cannon can be dangerous and should be not and should not be constructed, I left out a not, without proper training and experience. I am not saying you should go home and do this, okay? So let's just look at the problem though. Let me get it set up for you. All right, so what am I supposed to do? I'm trying to find the delta E, okay? What is the delta E? So what's my Q? How much heat? It is producing 1422 joules of heat. Is it releasing energy? Is it hot to the surroundings, or is it getting cold from the surroundings? I think you'd agree it's going to be hot. So what kind of sign should the 1422 be? Negative. So the burning of the fuel performs that much work on the potato. So if the system is the fuel, it's doing work on the potato, what would be the sign of the work would be? I think you'd agree it's also negative. Why is the heat negative? Because it's getting hot. Why is the work negative? Because it's doing work on the potato. So what will that equal? That will equal negative 200 or 2,277 joules. So let me kind of show you a graph that kind of goes along with this. Remember this graph from before? So what does this mean? That the E of the system is losing. Final minus initial is going to be a negative number. So that means the energy of the system starts off high, loses energy, and becomes lower. How much lower? That much lower. So that means if I take EF minus EI, I get a negative 2,277 joules. Okay, let's look at problem number 6. So a cylinder and a piston assembly defined as a system is warmed by an external flame. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against the external pressure. If the system absorbs 559 joules, I left out the joules, and does 488 joules of work during the expansion, what is the value of E? So what is delta H going to be? So if it's absorbing it, all right, what happens here? That it's going to be a positive, right? So what about it's doing so much work? If it does work to the surroundings, is that a positive or negative work? Hopefully you said it's a negative work, all right? It's going from the system to the surroundings. So if you do your math, you have your calculator handy, maybe you can do it with mental math, all right? Oops, you should get positive 71. So even though your thermal energy is positive, your work is negative, your overall is a positive. So what will my graph look like? Well, if it's positive, EI starts lower, it gets higher, and so here's my final value. So final minus initial is a positive 71 joules, okay? Why don't you do problem number 7, and let's see what you get. Welcome back. Hopefully you worked on this. So a chemical system produces 155 kilojoules of heat. So if it's producing it, it's releasing it, it's negative, and does 22 kilojoules of work. So again, if it's doing work, it's a negative value. What's the delta E for the surroundings? So what am I going to calculate first? I want to find out the delta E for the system, because I can calculate that, and I get negative 177. So what is the delta E of the surroundings? Well, it's the negative value. So what's negative times negative 177 is positive 177. Or look what I did here. So if the system releases 155 kilojoules, that means the surroundings absorbs. That's a positive. If the system does 22 kilojoules of work on it, that means that it was done to the surroundings. All right, so it's going to be a positive. And I get a positive 177, which is what I got up here, which is the opposite of this. So I believe that is the end of 6.3 part 2. And it's the end of section 6.3, so I will say it once again, don't wait to be great. We'll see you next time when we do section 6.4. Take care, bye-bye.